Tonight we're going to follow one of the strangest and most enchanting questions in all of science. Could life on Earth have begun somewhere else? Could the very first spark of biology have arrived here, carried across the silent gulfs of space? This idea has a name, the panspermia theory, and it suggests that the story of life may be bigger, older, and more mysterious than we usually imagine. Over the course of this journey, we'll explore how life might travel from one world to another, what kinds of cosmic vehicles could deliver it, and what experiments have shown about the survival of life in space. We'll look at meteorites that have fallen to Earth carrying complex organic molecules and ask whether they might be telling us something about our origins. And we'll consider what it would mean if the seeds of biology were scattered not just across our solar system, but across the entire galaxy. If you enjoy these gentle journeys through the cosmos, you can like this video and subscribe, or simply share a thought down in the comments. It helps others find their way here too. But for now, settle in, slow down, and let's begin. The word panspermia comes from the Greek roots pan, meaning all, and sperma, meaning seed. The concept has ancient echoes. Philosophers in antiquity, such as Anaxagoras, wondered whether the seeds of life might drift through the cosmos. But the modern scientific version of panspermia begins with the Swedish scientist Svante Arrhenius in the early 1900s. Arrhenius proposed what he called radiopanspermia, the idea that microscopic spores, so small and light, might be pushed across space by the pressure of starlight. He believed that hardy bacterial seeds could ride on beams of radiation, traveling between star systems, and perhaps finding their way to fertile planets. The idea fascinated and unsettled people in equal measure. It was both poetic and disconcerting, a suggestion that Earth might not be as self-contained as we thought. Through the 20th century, scientists revisited the theory in new forms. Francis Crick, co-discoverer of the structure of DNA, even speculated about directed panspermia, the possibility that life was intentionally seeded here by an advanced civilization. Today, panspermia remains on the fringe of consensus science, but it has never disappeared. Instead, it has evolved, shifting from bold speculation to a set of testable, if difficult, hypotheses. Modern space missions, sample returns, and laboratory experiments keep adding pieces to the puzzle enough to ensure that the idea is never fully dismissed. Scientists usually describe three broad flavors of panspermia. The first, lithopanspermia, is the most grounded in physics. In this scenario, rocks ejected from a planet by powerful impacts carry microbes hidden inside. Protected by stone, these tiny travelers might endure long journeys through space before crashing down on another world. Studies of meteorite exchange between Earth and Mars show that this process really can happen. Rocks from Mars have landed here and vice versa. The second, radiopanspermia, is Arrhenius' original idea. Spores or cells, small enough to be influenced by radiation pressure, could be swept across into stellar distances. The challenge here is harsh exposure. Without shielding, ultraviolet radiation, cosmic rays, and extreme cold likely destroy fragile molecules in relatively short times. Still, experiments continue to test just how long life might survive in open space. The third, directed panspermia, is more controversial. It suggests that life on Earth might have been deliberately seeded by an intelligent civilization. Francis Crick and Leslie Orgel raised this idea in the 1970s, not because they believed it was likely, but to provoke thought about life's ultimate origins. Some modern researchers have speculated in a similar vein, though most treat it as science fiction rather than mainstream science. Together, these three modes form a spectrum, from plausible to possible to provocative. And they remind us that panspermia is less a single theory than a family of related ideas, each asking the same daring question. What if life is more mobile than we think? Why dwell on panspermia at all? Isn't it enough to study life's chemistry here on Earth? The importance lies in the bigger picture. If panspermia has played a role, it changes how we think about our place in the cosmos. If life began elsewhere and found its way here, then our ancestry is not strictly terrestrial. Our family tree would have roots stretching back beyond Earth itself, perhaps to Mars, perhaps to an icy moon, perhaps even to another star system. This would mean that the story of biology is older than our planet, and that life is not a local accident, but a galactic traveler. Another reason is uniqueness. If life can spread between worlds, then its appearance might not be as improbable as some believe. Instead of being confined to one rare cradle, life could seed many environments across the galaxy. Each world would not need to reinvent biology from scratch. It could inherit a starter kit. That idea makes the universe feel more alive, more connected, and more filled with potential kin. Finally, panspermia forces us to confront the boundary between here and out there. Earth is not sealed off. It exchanges material with the solar system all the time. Meteorites fall daily. Dust rains down constantly. The universe is porous. And if molecules or even microbes can survive the journey, then the barrier between worlds may be thinner than we think. Among scientists, panspermia occupies a delicate position. It is not widely accepted as the explanation for life's origin on Earth, but neither is it dismissed as pure fantasy. Instead, it is treated as a possibility that deserves testing. Most mainstream researchers agree that lithopanspermia, the exchange of rocks between planets, is entirely plausible. We have physical evidence that it happens, and models show that microbes shielded inside rocks could, in principle, survive the trip. What remains uncertain is whether any actually did. Radiopanspermia, while imaginative, is harder to support. The exposure to radiation and timescales involved seem overwhelming for fragile biology. Experiments in low Earth orbit have shown survival for months or years, but not the millions of years needed to cross interstellar gulfs. Directed panspermia is the least accepted in the scientific community. It crosses into speculation about alien intent, and without evidence, most researchers leave it to philosophy and science fiction. Where caution is required is in fringe claims, announcements of alien microbes in meteorites, or mysterious red rains carrying supposed extraterrestrial cells. These have almost always collapsed under scrutiny, reminding us that extraordinary claims demand extraordinary evidence. One misconception about panspermia is that it attempts to replace the idea of a biogenesis, the natural origin of life from non-living chemistry. In reality, many scientists who discuss panspermia see it as a complement rather than a competitor. Abiogenesis remains the most widely studied explanation for life's beginnings. Experiments continue to explore how simple molecules might assemble into complex polymers and how polymers might become self-replicating systems. Panspermia does not make these questions vanish. Instead, it relocates them. If life came from space, it still had to begin somewhere. Think of it like tracing a river to its source. Abiogenesis describes the spring, the place where chemistry first tipped into biology. Panspermia asks whether that spring bubbled up on Earth itself or on another world. It doesn't remove the need for abiogenesis. It only changes the address. In fact, panspermia could even make abiogenesis more plausible. If multiple worlds were attempting the experiment at once, Mars, icy moons, distant planets, then the odds of success rise. Life might have emerged in many places, with only some of those beginnings finding fertile ground. Earth, in this view, is not a singular miracle, but part of a wider network of attempts. This synthesis keeps both questions alive. How does life begin, and how far can it travel? Now that we've defined what panspermia is and where it sits in scientific thought, we can begin to ask, what evidence do we have? This is where the theory moves from philosophy into the realm of testable science. The first line of evidence comes from physics. We know impacts on planets are violent enough to launch rocks into space. We know meteorites from Mars have landed on Earth, carrying within them traces of Martian chemistry. If rocks can move between worlds, the vehicle exists. The second line of evidence comes from biology. Certain organisms, bacterial spores, lichens, tardigrades, have demonstrated remarkable resilience. They can survive extremes of cold, vacuum, and radiation. Experiments on the International Space Station have shown survival for years outside protective shielding. These are hints that biology may be tougher than we once imagined. The third line comes from chemistry. Meteorites have been found with amino acids, sugars, and nucleobases, the building blocks of life. Recently, sampler-returned missions from asteroids like Ryugu and Bennu have confirmed the presence of organic molecules, including uracil, one of the letters of RNA. While these are not signs of life itself, they show that space is rich in the ingredients of life. And then there are the questions still open. Could microbes really endure the full journey? Ejection, space transit, and atmospheric entry intact? How long can life survive in space before radiation dismantles it? If life arrived here from space, why have we not yet found traces of similar life elsewhere? In the chapters to come, we'll follow these lines of inquiry: the mechanics of transfer, the endurance of biology, the couriers that could carry life, and the experiments that might finally test the idea. Step by step, we'll weigh the balance of possibility until we can see how close or how far panspermia might be from the truth. When a planet is struck by a large asteroid, the energy released is staggering. Rock shatters, shock waves race through the crust, and debris is hurled skyward at incredible speeds. Most of this material falls back down, but some fragments cross a threshold. They are launched with enough velocity to escape gravity's pull. This is where the concept of spallation windows comes. In the upper layers of rock near the impact site, fragments can be blasted free with surprisingly low heating. If conditions are just right, a chip of rock can break off, accelerate outward, and remain cool inside. If conditions are just right, a chip of rock can break off, accelerate outward, and remain cool inside, shielding whatever is buried within. For biology, this narrow path is critical. Too close to the surface, and the rock vaporizes too deep, and it never leaves the ground. But in between lies a window where microbes might hitch a ride to the stars. We know ejection happens because we've collected Martian meteorites on Earth. These are tangible proof that material can travel from one world to another. If rocks can move, the next question follows naturally. Can life move with them? Once freed into space, fragments enter an environment utterly unlike the world they left. The vacuum strips away air and water. Temperatures plummet, turning everything into a deep freeze. Radiation from the sun and cosmic rays bombard every exposed surface. And then there is time. Journeys between planets can last thousands to millions of years. For unprotected molecules, this is a death sentence. Ultraviolet light slices bonds apart in seconds. Cosmic rays slowly grind DNA into fragments. Yet inside a thick enough shield of rock, conditions are less hostile. A few centimeters of stone can cut radiation to survivable levels. Spores, dried and dormant, might last astonishing spans if they remain hidden. Experiments with spores exposed on the outside of the International Space Station have shown survival for years. In the deep interior of a meteorite, survival times might stretch into the millions. The transit stage is brutal, but not automatically fatal. Biology's toughest survivors could, in theory, drift in silent suspension, waiting for the next encounter. A fragment's odyssey is not complete until it meets another planet. But this final stage, atmospheric entry, is arguably the most dangerous. Traveling at tens of kilometers per second, the rock slams into air, generating a fireball of heat and light. The outside melts or vaporizes. The shock is intense. And yet, once again, shielding matters. Large meteorites act as natural heat shields. Their interiors remain cool even as their surfaces incinerate. If microbes were buried deep, they could emerge untouched. Laboratory tests have confirmed this. In one experiment, spores sealed inside artificial meteorites survived fiery re-entry when carried back from space on orbital capsules. Landing is the last hurdle. A catastrophic impact can sterilize everything. But smaller pieces slowed by atmosphere can fall gently, scattering across the surface. The odds are slim, but across geological timescales, even slim odds become meaningful. Arrival is the gauntlet, but not an impossible one. Space is not empty chaos. Orbits, resonances, and gravitational pulls create corridors of movement, what scientists call dynamical highways. When rocks escape from a planet like Mars, their paths are not random. Many are guided by these highways, steering them into orbits that eventually cross Earth's. Computer models show that transfers between Earth and Mars can sometimes happen astonishingly quickly. While most rocks take millions of years, a small fraction can arrive within a few decades. These rare, fast routes are crucial because they keep survival windows short enough for hardy microbes to stand a chance. Jupiter plays a key role too. Its immense gravity can fling rocks out of the solar system or nudge them inward toward the terrestrial planets. The solar system is dynamic and interconnected, and in its motions there are opportunities for matter and perhaps life to flow between worlds. In 2017, astronomers spotted something unprecedented, a cigar-shaped object tumbling past the sun, moving too fast to be from our solar system. It was named Oumuamua, a messenger from afar. Just 2 years later, another visitor arrived, Comet Borisov, streaming gas and dust like a classic comet, but on a trajectory that revealed its interstellar origin. These discoveries changed how we think about panspermia. Interstellar objects are not once-in-an-eternity flukes. They are common, passing through the solar system regularly. If they carry ices, organics, or even dormant life, they could be carriers linking star systems across the galaxy. The numbers are still uncertain, but estimates suggest that trillions of such objects wander between the stars. If only a fraction carry the seeds of biology, then the exchange of life between star systems, though unlikely for any one rock, might, across billions of years, be a real contributor to the spread of life. The most romantic version of panspermia is also the most fragile, radiopanspermia. In this scenario, tiny spores are so light that the pressure of starlight can push them out of one star system and into the interstellar void. On paper, the physics works. Radiation does exert pressure, and dust grains are known to be carried outward on these streams of light. But biology is not paper. A spore exposed directly to starlight faces a harsh bath of ultraviolet radiation capable of shredding DNA and proteins in minutes or hours. Cosmic rays add another layer of destruction, breaking chemical bonds relentlessly over long spans. Even if a spore began its journey intact, the time halos involved, millions of years to cross interstellar distances, make survival seem vanishingly small. Laboratory tests support this grim assessment. When microbes are exposed in orbit without shielding, most perish quickly. A few hardy survivors linger for months or years, but nowhere near the lifetimes needed for interstellar journeys. Shielding within ice or dust could extend the odds. But at that point, the mechanism becomes closer to lithopanspermia than to the original vision. This does not make radiopanspermia useless. Instead, it serves as a poetic thought experiment. It reminds us that the universe is filled with motion, but light itself can carry matter outward, and that in principle, even the tiniest grains can drift across vast gulfs. Whether they carry viable life is another matter. The current consensus is that radiopanspermia, though evocative, is unlikely to be the source of life on Earth. Still, its legacy endures as the earliest scientific articulation of panspermia and as a symbol of the imagination needed to explore such cosmic questions. Life has a remarkable trick up its sleeve: dormancy. When conditions grow hostile, certain organisms do not struggle against the storm, they simply pause. Bacterial spores are perhaps the most extreme example. Inside a tough protein shell, with DNA tightly wound and water content reduced to almost nothing, they can wait. Heat, cold, desiccation, radiation, all slow their damage when metabolism is frozen. Spores have been revived from ancient salt crystals millions of years old, still viable after geological slumber. Seeds are a parallel marvel. Though more complex than spores, many plants package their embryos in shells of armor and nourishment, designed to ride out winters, droughts, and even fire. A lotus seed retrieved from a dry lake bed was coaxed into growth after more than 1,000 years. These are not adaptations for space travel, but they hint at biology's hidden toughness. If an organism can survive burial in salt for millennia, perhaps it could also survive entombment in rock during a long voyage through space. Dormancy does not guarantee survival, but it stretches the odds. The champions of dormancy remind us that life has already evolved solutions for waiting and waiting and waiting until conditions improve. Speculation is one thing, experiments are another. To test the limits of survival in space, researchers have carried organisms to the International Space Station and left them exposed to the raw environment. These trials, known collectively as expose missions, have placed microbes, lichens, algae, and even simple animals outside the station for months or years. The results are sobering but also astonishing. Many organisms die quickly under unfiltered ultraviolet light. Yet when shaded or when tucked into protective layers, some survive for years. Bacterial spores sealed within tiny cracks or encased in simulated rock endured up to 6 years in orbit. Even delicate lichens, scraped from the sides of rocks on Earth, resumed photosynthesis after nearly 2 years outside the station. The Japanese-led Tanpopo experiment expanded this work, specifically studying how microbes might hitchhike on dust particles in space. Microbe samples were mounted on the outside of the station, both bare and protected, for spans of up to 3 years. When retrieved, some remained viable. This demonstrated that microbial passengers could, in principle, endure long enough to move between planets, if shielded by even thin layers of dust or stone. What these trials reveal is a gradient of possibility. Bare life, directly exposed, is shredded by ultraviolet light in weeks. But hidden life, shielded in tiny shelters, can endure for years. A time scale long enough for short transfers between nearby planets, especially if dynamical highways speed the journey. No one experiment has yet proven that life could survive millions of years in space. But the fact that survival is measurable at all, even across years in low Earth orbit, turns panspermia from fantasy into a testable scientific idea. It shows us that biology, though fragile, also has unexpected resilience when given even a thin refuge. For sheer endurance, few creatures rival the tardigrade. Tiny, plump-bodied animals with 8 stubby legs and an endearing shuffle. When conditions become dire, tardigrades can enter a cryptobiotic state known as atun, in which they retract their legs, expel most of their water, and halt metabolism almost entirely. In 2007, scientists put this resilience to the ultimate test by sending tardigrades into open space. Exposed for 10 days to vacuum, radiation, and unfiltered ultraviolet light. Many perished, but some survived, later rehydrating and reproducing back on Earth. This was the first demonstration that an animal, not just microbes, could endure direct exposure to space, even if only briefly. Tardigrades are not candidates for cosmic hitchhikers. Their survival times are short compared to the spans required for interplanetary or interstellar transfer. But they serve as boundary markers. If even a multicellular animal can survive days to weeks, then it is not unreasonable to imagine that simpler, hardier forms, bacteria, spores, lichens, might survive vastly longer when protected. Tardigrades remind us that life does not always collapse under stress. Sometimes it simply contracts, waits, and emerges again. Leaving a planet is violent, a rock blasted into space by an asteroid. Impact experiences crushing acceleration and searing heat. For panspermia to work, life must survive not only space itself, but also the extreme stresses of launch and landing. To test this, scientists have fired microbial spores into rock samples and blasted them with high-velocity projectiles, simulating the shock of impact. Some spores survived accelerations tens of thousands of times Earth's gravity. The outer layers were sterilized, but deep within cracks and pores, life persisted. Re-entry is another crucible. Temperatures soar as meteorites blaze through atmosphere. But experiments embedding spores in heat-shielding materials have shown survival. In one test, samples returned from orbit on capsules survived fiery descent, emerging intact. In another, spores buried in artificial meteorites endured simulated re-entry in laboratory furnaces. These results point to a narrow but real survivability window. Not every spore would make it, not even most. But across billions of years, with countless impacts and countless ejections, even rare survivals add up. Biology does not need certainty, only possibility, repeated often enough. Shock and heat reduce the odds, but they do not reduce them to zero. Radiation is relentless. Cosmic rays slice through molecules, breaking DNA strands. Ultraviolet light cracks chemical bonds. For biology in transit, the real threat is not instant death, but slow accumulation of damage. Over thousands of years, mutations mount until genetic information is scrambled beyond repair. Yet biology is not defenseless. Spores contain specialized proteins that protect DNA from breaking apart. Some microbes have extraordinary repair systems that reassemble shattered genomes when conditions improve. Dunococcus radiodurans, nicknamed Conan the bacterium, can stitch its DNA back together, even after doses of radiation that would kill humans many times over. The key is time. If transfer between worlds takes decades or centuries, survival seems plausible. If it stretches to millions of years, the burden of mutations grows overwhelming, even for the hardiest organisms. Transit is therefore a race between the pace of radiation damage and the pace of transfer. Survival depends less on perfection than on whether the biological time budget outlasts the cosmic journey. As scientists have explored the solar system, they've had to face a sobering thought. If life can survive space travel, then our spacecraft might become accidental couriers. A lander that isn't perfectly sterilized could deliver Earth microbes to Mars or Europa, contaminating environments we hope to study. This concern has led to strict planetary protection protocols. Spacecraft destined for potentially habitable worlds are painstakingly cleaned, baked, and tested to minimize microbial stowaways. The rules are not perfect, No sterilization is absolute, but they reflect how seriously scientists take the possibility of interplanetary contamination. Planetary protection is also about reciprocity. If we someday return samples from Mars or Europa, they must be quarantined to avoid introducing alien microbes here on Earth. Whether or not panspermia has already happened, the possibility changes how we explore. It reminds us that life, once it exists, is remarkably persistent, and that curiosity must always walk hand in hand with caution. Every single day, Earth is bombarded by material from space. Most of it is invisible, grains of dust no bigger than sand, burning harmlessly as shooting stars. But larger pieces also fall, meteorites that survive their descent and reach the ground. Altogether, tens of thousands of tons of extraterrestrial matter rain down on our planet each year. These meteorites come in many forms. Some are metallic, forged in the hearts of asteroids. Others are stony with textures resembling ancient volcanic rock. A precious subset, the carbonaceous chondrites, are dark and fragile, rich in carbon compounds. These are the ones scientists prize most because they contain chemistry that predates Earth itself. What makes meteorites especially important for panspermia is their interior. As they blaze through the atmosphere, their outer layers melt and vaporize, but their cores remain shielded. Inside, temperatures can stay close to the cold of space. Any molecules, or in principle microbes, buried within would be protected during the fiery plunge. Meteorites are not just falling rocks. They are natural delivery capsules. Each one is a messenger, carrying chemistry from elsewhere in the solar system, and occasionally, perhaps, the galaxy. In 1969, a fireball lit up the skies above southeastern Australia. Fragments rained down near the town of Murchison, and locals gathered the blackened stones. Scientists soon realized what they had: a carbonaceous chondrite fresh from space, remarkably unweathered by Earth's environment. The Murchison meteorite would become one of the most studied rocks in history. When chemists analyzed it, they found something extraordinary. Inside were over 70 different amino acids, the building blocks of proteins. Many were familiar, matching the ones used in biology. Others were exotic, not part of earthly life. Their presence showed that complex organic chemistry can happen spontaneously in space without living organisms. Even more intriguing was chirality. Amino acids can exist in two mirror image forms, left-handed and right-handed. Life on Earth uses almost exclusively left-handed versions, a mystery known as homochirality. In Murchison, scientists found a slight excess of left-handed amino acids. This hinted that cosmic processes might tilt chemistry in the same direction as biology, offering a possible clue to why life chose one hand over the other. The Murchison meteorite demonstrated that meteorites are not sterile lumps of rock. They are chemical laboratories, frozen records of reactions that occurred before Earth was born. Its amino acids suggested that at least part of life's toolkit arrived ready-made from space. Whether or not microbes ever hitched a ride, the chemistry alone made Murchison a cornerstone in the case for panspermia. Murchison was only the beginning. Other meteorites have revealed different, equally tantalizing treasures. In 2000, a brilliant fireball streaked across the skies of Canada and exploded over frozen Tagish Lake. Locals retrieved fragments that landed on ice, minimizing contamination. Analyses showed that Tagish Lake was rich in organic compounds, including unusual hydrocarbons and amino acids. Its composition was distinct from Murchison, demonstrating that different parent bodies in the solar system brew their own varieties of organics. The Orgueil meteorite, which fell in France in 1864, is another famous example. It was a fragile carbonaceous chondrite that quickly crumbled, but it too contained a suite of organic molecules. Early claims that it harbored microfossils were eventually debunked, but its chemistry was undeniable. Orgueil, like Murchison and Tagish Lake, carried an inventory of building books that blurred the line between geology and biology. Together, these meteorites remind us that organics are widespread in space. They are not flukes, but recurring themes. Each fall is a glimpse into the diversity of prebiotic chemistry scattered through the solar system. Chemistry that could have primed the early Earth for life. For decades, scientists studied meteorites after they fell. But contamination was always a problem. Earth's air, water, and life quickly infiltrate fragile samples, leaving doubt about what is truly extraterrestrial. That's why sample return missions are such a leap forward. They collect pristine material directly from asteroids and bring it back sealed. Japan's Hayabusa 2 mission visited the asteroid Ryugu in 2018. It fired a small projectile into the surface, collected the debris, and safely delivered it back to Earth in 2020. When scientists opened the capsule, they found dark grains rich in carbon. Within them were amino acids, nuclear bases, and most notably, uracil, one of the 4 bases of RNA. This was the first direct proof that a fundamental ingredient of genetic material exists on an asteroid. Ryugu also contained niacin, or vitamin B, a compound critical to metabolism. These molecules suggested that asteroids are more than random rocks. They may be reservoirs of biological precursors. NASA OSIRIS-REx mission to asteroid Bennu took this a step further. In 2023, it returned samples that are still being studied. Early results show abundant organics, including unexpected compounds like magnesium-sodium phosphates. These phosphates are essential to DNA, RNA, and cell membranes. Their presence in Bennu's rubble adds a striking new piece to the puzzle. The chemistry of life is not confined to Earth. It is written into the fabric of primitive asteroids. Together, Ryugu and Bennu provide the cleanest evidence yet that the ingredients for biology are widespread. These missions don't prove panspermia in the sense of living organisms traveling through space, but they show that space delivers chemistry and perhaps much more. With every sample, the line between Earth's biology and the wider cosmos becomes thinner. While meteorites and asteroids link Earth to the solar system, panspermia also raises a more daring possibility: exchange between star systems. For this to happen, interstellar objects would need to carry chemistry, or even microbes, across light years. For centuries, this was pure speculation. But in 2017, astronomers detected Oumuamua, the first known object from beyond the solar system passing through ours. It was elongated, tumbling, and unlike anything seen before. 2 years later, Comet Borisov arrived, a more familiar visitor with a gaseous tail. But again, its trajectory revealed interstellar origins. These discoveries prove that interstellar objects are not rare. Models now suggest trillions drift between stars, with many crossing planetary systems every year. Could such visitors carry organics? Almost certainly. Comet Borisov's spectrum showed carbon-based compounds in its coma, consistent with a rich chemistry. Could they carry dormant microbes? That remains far less likely, given the immense timescales and harsh exposure of interstellar space. Still, the possibility cannot be dismissed outright, especially if fragments are shielded within ice or rock. The greater significance lies in the principle. If interstellar couriers are common, then the galaxy is more interconnected than we imagined. Over billions of years, materials could be exchanged not only within solar systems, but between them. Even if life does not leap such gulfs, chemistry certainly can. Every interstellar visitor that passes through is a reminder that panspermia is not confined to our neighborhood. It is, in theory, a galactic process. Of all the potential exchanges of life in the solar system, the most plausible is between Earth and Mars. The two planets sit relatively close, their orbits bringing them into alignment every couple of years. Both have been bombarded by asteroids and comets for billions of years, sending debris flying into space. Some of that debris inevitably makes the journey from one planet to the other. The evidence is literally in our museums. We have found meteorites on Earth that came from Mars. They are recognizable by their unique isotopic fingerprints. Tiny bubbles of gas trapped inside match the Martian atmosphere measured by Viking landers in the 1970s. These Martian meteorites prove that rocks can travel from Mars to Earth. The reverse is also true. Computer models show that Earth ejecta can land on Mars. But how often does this happen, and how quickly? Simulations suggest that millions of kilograms of Martian rock have landed on Earth over geological timescales. Some fragments can arrive astonishingly fast, within 20 years of ejection. Others may wander for thousands or millions of years before encountering our planet. The quick transfers are crucial. If a microbe is sheltered deep inside rock, surviving a journey of decades is challenging, but possible. Surviving millions of years is far less likely. If Mars ever hosted life, its microbes could have traveled to Earth. If Earth developed life first, the same process could have seeded Mars. This raises a profound possibility that life on both planets, if it exists, may share a common origin. Future Sun Pillar return missions may one day test this idea, comparing Martian biology directly with our own. Venus is often imagined as Earth's evil twin, the same size, the same composition, but cloaked in thick, crushing atmosphere and surface temperatures hot enough to melt lead. Yet far above that infernal surface, in the temperate cloud decks 50 kilometers up, conditions are surprisingly gentle. Temperatures are near room level and pressures are similar to Earth's. Some researchers have speculated that microbes could persist in these clouds, drifting on droplets of sulfuric acid. In 2020, a controversial report claimed detection of phosphine gas, a possible signature of life, though subsequent studies cast doubt on the finding. Still, the idea lingers that Venus's atmosphere might be a temporary refuge or even a stopover point for life blown from planet to planet. While no direct evidence yet supports this, the possibility adds Venus to the list of worlds worth watching. If biology can survive in its acid clouds, panspermia might not require solid ground at all. Far from the sun, icy moons hide oceans beneath their frozen crusts. Saturn's moon Enceladus has geysers that erupt through surface cracks, spraying water vapor and ice into space. NASA Cassini spacecraft flew through these blooms and found salts organics, and, in a stunning discovery, sodium phosphates, essential ingredients for life's biochemistry. This means Enceladus's hidden ocean is not only liquid, but chemically rich, a potential cradle for biology. Jupiter's moon Europa is another candidate. Its cracked, streaked surface covers a global ocean thought to be deeper than all Earth's seas combined. Observations suggest that plumes may also erupt from Europa, though less frequently than at Enceladus. Beneath the ice, interactions between water and rock may provide energy and nutrients much like Earth's deep-sea vents. For panspermia, these moons matter in two ways. First, they are potential homes for life. If microbes exist in their oceans, geysers could eject them into space, where they might be picked up by passing debris. Second, they are destinations. Rocks or dust carrying microbes from elsewhere could seed their oceans if they penetrate the ice. Enceladus and Europa remind us that habitability is not limited to planets. Small moons with hidden seas and volcanic activity may be just as welcoming, and perhaps even more likely to exchange biology through their constant venting into space. Titan, Saturn's largest moon, is a world unlike any other. It has thick golden clouds, a dense nitrogen atmosphere, and lakes and rivers, not of water, but of liquid methane and ethane. Standing on its surface would feel surreal. Rivers cut channels across the land, but they flow with hydrocarbons in a deep freeze hundreds of degrees below zero. At first glance, Titan seems inhospitable to life as we know it. Water is locked away as rock-hard ice. Temperatures are far too cold for conventional biology. And yet Titan has the raw ingredients. Complex organic molecules form in its atmosphere and rain down to the surface. NASA Cassini spacecraft detected pollens, tar-like residues made of nitrogen and carbon, blanketing its landscape. Could such chemistry one day lead to life? Some scientists argue Titan is a prebiotic laboratory, showing us alternative pathways to complexity. For panspermia, Titan's importance is symbolic. It proves that life's building blocks emerge even in exotic alien environments. Whether or not Titan hosts life today, it stands as a reminder that the universe is filled with surprising chemistries that could feed into the larger cycle of seeding and exchange. When we look back full billion years, the solar system was not the calm clockwork we see today. It was a chaotic shooting gallery. Asteroids and comets slammed into planets with far greater frequency. The giant impact that formed Earth's moon was only one of many colossal collisions. Smaller impacts were constant, blasting debris into space and scattering it across the inner solar system. In that environment, Earth, Mars, and Venus were not isolated islands, but nodes in a connected network. Material was constantly exchanged between them. Models suggest that in the first few 100 million years, billions of tons of rock moved back and forth. If life or prebiotic chemistry existed anywhere, it would have had ample chances to spread. This vision turns the early solar system into something like a microbial archipelago, a set of worlds linked by constant exchange. Life might not have needed to arise on each world separately. Instead, one successful origin could seed its neighbors, creating a family of biospheres with shared ancestry. Even if life never emerged, the chemistry itself circulated. Amino acids and other organics, delivered by comets, could be shared between Earth, Mars, and Venus, enriching each world's inventory. The idea of a connected ecosystem shifts the story of life's origins from a single spark on a single planet to a broader drama playing out across an entire region of space. Timing is everything. For panspermia to work, not only must transfer be possible, it must align with the right conditions. Early in the solar system's history, heavy bombardment provided frequent opportunities for exchange. Debris was abundant and travel routes between planets were shorter and more chaotic. At the same time, planets were cooling, oceans were forming, and atmospheres were stabilizing. These were windows of opportunity, periods when environments were becoming habitable, just as the traffic of rocks and organics was at its peak. If life began on one world slightly earlier, its export to others could have been rapid. Today, the solar system is quieter. Impacts are rarer, exchanges slower. The window for frequent seeding has largely closed. The billions of years ago, the timing may have been perfect. A burst of activity at exactly the moment when worlds were ready to receive and nurture the fragile beginnings of life. When thinking about panspermia, one way to gauge plausibility is to ask a simple question: how many opportunities are there? Even if survival odds are slim, sheer numbers may tip the balance. This is where a Fermi-style estimate helps, breaking a vast uncertainty into smaller, more manageable steps. Let's begin with impacts. Large asteroid strikes on Mars and Earth have occurred countless times over the past 4 billion years. Each impact can launch billions of kilograms of debris into space. Simulations suggest that millions of rocks, ranging from tiny pebbles to boulders tens of meters across, have been flung from Mars alone. Next, how many of these fragments actually intersect Earth's orbit? Models indicate that about 1 in 100 makes the crossing. That still leaves tens of thousands of potential couriers per major impact. Now, of those, how many would land softly enough to deliver a viable cargo? Perhaps only a handful. But with thousands of opportunities, even a handful can add up. Finally, consider time. Over billions of years, impacts repeat again and again. Even if only a tiny fraction of all ejected rocks carry viable life, the cumulative number of attempts becomes enormous. And spermia does not need to work often. It only needs to work once. A single successful delivery could alter the course of planetary history. The gap between ejection and arrival is filled with one factor above all: time. Transit durations determine whether survival is plausible or impossible. If a rock takes only a few decades to travel from Mars to Earth, spores sheltered inside might endure. If the journey stretches to millions of years, survival chances collapse. Computer models show a wide distribution. Some ejecta reaches Earth quickly, in as little as 20 years. Others wander for thousands or even tens of millions before striking. The average case is grim, but the tail end of the distribution, the rare rapid transfers, is what matters most. Now weigh this against biology's half-lives. Dormant spores degrade slowly, but not infinitely. Radiation, chemical instability, and molecular breakdown accumulate. A common estimate is that DNA has a half-life of about 500 years under normal conditions. Shielding extends this considerably, but not forever. After 1 million years, most genomes would be unrecognizable fragments. And yet, the quick transfers are realistic. A tiny percentage of rocks make the crossing in under a century. For biology, this window is survivable. For panspermia, it is enough. Life does not need to survive every journey. It only needs to be lucky occasionally. Time is a filter, but it is not an absolute barrier. The statistics of transit overlap just enough with the resilience of biology to keep the hypothesis alive. Even with shielding, space is hostile. 3 choke points loom largest: ultraviolet radiation, desiccation, and chemical decay. Ultraviolet light slices through DNA in seconds, breaking bonds and scrambling instructions. A bare spore exposed to direct sunlight in space would be sterilized almost instantly. Shielding is essential. Just a millimeter of dust can make the difference between destruction and survival. Desiccation is another threat. In vacuum, water evaporates, leaving cells brittle and prone to molecular fractures. Spores counter this by drying themselves deliberately, packing DNA with protective proteins that stabilize structure. Still, desiccation is not perfect. The longer it lasts, the more cracks appear. Finally, spontaneous chemical decay happens regardless of environment. Bonds slowly break, bases mutate, and molecules unravel. This process is glacial, but over thousands of years it accumulates. Even without radiation, biology has a shelf life. Together, these choke points form a gauntlet. They do not make survival impossible, but they lower the odds with every passing year. For panspermia to succeed, shielding and rapid transit must align. Without both, even the hardiest spores eventually succumb. Reaching a planet is not the end of the story. Most rocks that cross Earth's orbit never strike the planet at all. They burn in the atmosphere or pass by harmlessly. Those that do land face another filter: conditions upon impact. A violent crash may shatter the rock and sterilize its contents. Only smaller fragments, slowed by atmosphere or landing gently in oceans, offer real chances of delivery. But suppose a fragment arrives intact, carrying viable spores. What then? For panspermia to matter, life must not only survive, but also thrive. The landing site must be compatible, not too dry, not too acidic, not instantly hostile. In Earth's early oceans, such a site might have been common. On Mars today, it may be vanishingly rare. Post-landing recovery is the most speculative stage. A few cells may survive, but unless they reproduce, their journey ends in silence. Successful panspermia is not just about survival. It is about colonization. The odds of this final step are impossible to quantify. But again, across billions of years, opportunities abound. If only one landing out of millions gave life a foothold, the result could be profound. Ultimately, then spermia lives in the space between models and experiments. Computer simulations can calculate how rocks move, how often they cross orbits, and how long they take. Laboratory studies can expose spores to vacuum, radiation, and shock. Each line of evidence provides a piece of the puzzle. Models say that exchange between Earth and Mars is not rare. Thousands of rocks have likely traveled between the two planets. Salmon journeys short enough to preserve biology. Experiments say that spores can survive in space for years, that they can endure shocks of launch and re-entry, and that shielding makes survival plausible. What we cannot yet test is the whole chain at once. No experiment has followed a real rock carrying real microbes across interplanetary space and back again. Until that happens, panspermia remains a hypothesis stitched together from partial evidence. It is neither confirmed nor ruled out. The models suggest it could work. The experiments suggest biology is resilient enough. Whether the two align in reality is still an open question. Life has a curious quirk. The molecules it uses are not symmetrical, even though chemistry in general is. Amino acids come in two mirror image forms, left-handed and right-handed. On Earth, living organisms use almost exclusively the L form. Why? There is no inherent reason in basic chemistry. If you mix amino acids in a lab, you get equal amounts of both. This puzzle is called homochirality and is as long intrigued scientists. If life began from a random soup of molecules, why should it prefer one hand over the other? Some suspect that the answer lies beyond Earth. Meteorites like Murchison provide tantalizing hints. Within their fragments, scientists have found amino acids with small but consistent excesses of the L form. The imbalance is subtle, a few percent, not the near total dominance of biology, but it is there. This suggests that cosmic processes, such as polarized radiation in interstellar clouds or chemical reactions on icy grains, can nudge chemistry toward one hand. If so, Earth may have inherited a pre-bias toolkit. The early oceans might have been seeded not with a perfect 50-50 mix, but with a starter set tilted toward the left. Once life began, natural selection could have amplified the bias into total commitment. The meteorite data does not solve the puzzle, but it shows that chirality is not an exclusively terrestrial trait. It is written, at least faintly, into the chemistry of the cosmos. Another way chemistry reveals its origins is through isotopes, variants of elements with different numbers of neutrons. Carbon, nitrogen, and hydrogen each have multiple isotopes, and the ratios between them act like fingerprints. These ratios vary depending on where and how molecules formed. For example, carbon on Earth exists mostly as carbon-12, with a small fraction of carbon-13. Biological processes favor lighter isotopes, leading to detectable shifts in ratios. Meteorites, by contrast, often show enrichment in carbon-13, reflecting their formation in cold interstellar conditions. Nitrogen tells similar stories. Some meteorites contain isotopic signatures, unlike anything found on Earth, hinting at origins in distant regions of the solar nebula. Hydrogen is perhaps the most striking. The ratio of deuterium-heavy hydrogen to normal hydrogen varies widely across the solar system. Water in comets, asteroids, and Earth's oceans can be compared to determine whether they share a common source. These isotopic passports allow scientists to trace the pathways of molecules across space and time. When we find unusual isotopic ratios in meteorites, we are seeing evidence of chemistry older than our planet, chemistry that traveled vast distances before being delivered here. In this way, isotopes serve as witnesses, tiny markers, showing that the ingredients of life carry stories of cosmic migration. Amino acids are only part of the picture. Life also requires sugars, nuclear bases, and phosphates, the ingredients of RNA, DNA, and metabolism. For decades, these seemed unique to Earth. But in recent years, discoveries have pushed their origins outward. The Ryugu samples returned by Japan's Hayabusa 2 mission contained leucine, one of the 4 bases of RNA. Alongside it was niacin, or vitamin B essential for metabolic processes. These finds were striking because the samples were pristine, sealed from Earth's contamination. They showed that nuclear bases form naturally on asteroids without biology. NASA OSIRIS-REx mission to asteroid Bennu brought back another surprise. Among its rich organic inventory were magnesium-sodium phosphates. Phosphates are critical to biology. They form the backbone of DNA and RNA, power metabolism through ATP, and build cell membranes. Their presence in Bennu's dust is a reminder that life's most fundamental components are not limited to Earth, but emerge spontaneously in primitive bodies. Even farther afield, Saturn's moon, Enceladus, provided perhaps the most dramatic discovery. Its geysers, sampled by the Cassini spacecraft, contained not only organics, but also sodium phosphates dissolved in plume particles. This confirmed that its hidden ocean is enriched with phosphorus, an element once thought scarce beyond Earth. Together, these discoveries sketch a universe rich in prebiotic chemistry. Sugars, nuclear bases, and phosphates are not rare accidents, but recurring outcomes of planetary and asteroid chemistry. They suggest that the ingredients of life are widely available, scattered across moons, asteroids, and comets, waiting for the right conditions to assemble into biology. Studying extraterrestrial chemistry comes with a constant challenge: contamination. Earth is filled with the very molecules scientists seek: amino acids, nuclear bases, sugars. Distinguishing what is truly alien from what leaked in after landing is difficult. This problem has haunted meteoritic studies. Some early claims of extraterrestrial life, including supposed microfossils and meteorites, collapsed once contamination was identified. Even the famous Murchison meteorite has been handled and studied for decades, raising the risk of earthly molecules sneaking in. To counter this, researchers rely on strict protocols. Samples are collected quickly, often frozen or stored in nitrogen. Isotopic analysis helps. Extraterrestrial organics often carry unusual isotope ratios, proving they did not originate on Earth. Even so, doubts linger. This is why sampler return missions are so valuable. By collecting and sealing material in space, they bypass Earth's biosphere entirely. Ryugu and Bennu's organics are compelling not only for what they contain, but for the confidence that they are untainted. In this sense, contamination control is not just a technical detail, but the key to trust. Without it, every extraordinary claim risks collapsing into ordinary error. Suppose panspermia is correct, or at least that Earth was primed with extraterrestrial ingredients. What evidence would we expect? First, we would expect meteorites to contain not just traces, but a full spectrum of prebiotic molecules, amino acids, nuclear bases, sugars, phosphates. This is exactly what has been found in carbonaceous chondrites and asteroid samples. Second, we would expect these molecules to show isotopic signatures inconsistent with earthly chemistry, pointing to origins in interstellar clouds or primitive solar system bodies. This too has been observed. We might also expect to see hints of biological bias, like the left-handed amino acid excesses in meteoroids. Such biases suggest continuity between cosmic chemistry and terrestrial life. Finally, we would expect Earth's timeline for life's appearance to be short. If life's seeds were delivered ready-made, biology could emerge rapidly once the planet cooled. Indeed, evidence suggests life began here astonishingly early, within a few 100 million years of Earth's formation. These signs do not prove panspermia outright, but they align with its expectations. They show that Earth was not isolated. It was a recipient of cosmic chemistry that may have tilted the odds toward life. But what if panspermia never happened? What if life's chemistry was entirely Earth's own? Then the evidence should tell a different story. In this scenario, extraterrestrial molecules may exist, but they are irrelevant background noise. Life's essential chemistry would have emerged independently in Earth's primordial environments, tidal pools, hydrothermal vents, or icy ponds. The amino acids in meteorites would be curiosities, not ancestors. The isotopic biases would be coincidental, not formative. We would expect the timeline for life to be slower, constrained by the pace of Earth's own chemistry. The fact that life appears early in the geological record could then be explained by rapid terrestrial abiogenesis, not external delivery. Homochirality would require an earthly explanation, perhaps asymmetric mineral surfaces, or self-reinforcing feedback loops in autocatalytic reactions. This view keeps life's story contained within our planet. It emphasizes independence over inheritance. The signs of extraterrestrial organics become decorations, not roots. And while it denies panspermia's role, it leaves intact the wonder of abiogenesis, the transformation of simple molecules into self-replicating systems, an emergence as profound as any cosmic delivery. In 1984, a team of geologists exploring the Allen Hills region of Antarctica found a peculiar rock. It was cataloged as ALH84, one of many meteorites collected from the ice. Years later, scientists realized it had come from Mars, blasted into space by an ancient impact and eventually landing on Earth. In 1996, this meteorite electrified the world. A NASA team reported structures within the rock that looked, under an electron microscope, like tiny fossils. These worm-like shapes, only a few hundred nanometers long, were interpreted by some as possible remnants of Martian microbes. The announcement made headlines, even prompting a televised statement by the US president at the time. But excitement soon gave way to doubt. Critics pointed out that the structures were smaller than the smallest known bacteria, raising questions about whether they could be biological at all. Other features of the rock, such as chemical signatures and magnetite crystals, were shown to have possible non-biological origins. Gradually, the consensus shifted. The evidence was intriguing but not conclusive, and most likely explained by inorganic processes. The ALHA4 episode remains a cautionary tale. Morphology, the appearance of shapes, can be seductive. Our eyes are quick to see life where none exists. Without rigorous chemical and isotopic confirmation, suggestive shapes in rocks are not enough. The meteorite reminded scientists and the public alike that extraordinary claims require extraordinary care, and that the line between fascination and misinterpretation is perilously thin. In the summer of 2001, unusual rain fell over the Indian state of Kerala. Locals reported showers of crimson-colored water that stained clothes and rooftops. The phenomenon sparked rumors and wonder. What could cause the skies to rain red? Some scientists suggested that the color came from fungal spores or algae swept into the atmosphere. Others, more provocatively, proposed an extraterrestrial origin. A small group of researchers argued that the red particles might be alien cells, delivered to Earth from space and falling as a literal rain of life. The story caught media attention and became entwined with panspermia speculation. Subsequent studies, however, revealed a more down-to-earth explanation. The red particles were spores from a local alga, blown high into the air during monsoon storms and washed down with rain. Their cell walls gave the water its startling color. Microscopy and chemical analysis confirmed that the particles were biological but entirely terrestrial. The red rain of Kerala stands as another cautionary example. An unusual phenomenon, striking in appearance, was swiftly framed as potential evidence for panspermia. But when tested carefully, the mystery dissolved into a natural process already known on Earth. The lesson is simple. Strange is not the same as extraterrestrial. Nature provides plenty of surprises without reaching beyond the planet. Both ALHA4 and the Red Rain episode highlight a broader truth. In the search for life beyond Earth, evidence must be handled with exceptional care. The stakes are high, and so are the risks of misinterpretation. Extraordinary claims, such as the discovery of alien microbes, cannot rest on ambiguous shapes or unexplained colors. They require multiple independent lines of evidence. Chemistry must match biology. Isotopes must rule out contamination. Experimental controls must be airtight. Without such hygiene, science risks fooling itself and misleading the public. This is especially important in panspermia research, where the boundary between speculation and fact is delicate. The history of false positives shows how easy it is for enthusiasm to outpace data. Each misstep not only erodes public trust, but also makes future genuine discoveries harder to recognize. Skepticism becomes sharper, and deservedly so. For this reason, planetary protection protocols, contamination controls, in-sampler return missions, and rigorous peer review are not just bureaucratic hurdles. They are essential safeguards. They ensure that when we do claim evidence of life beyond Earth, the case is overwhelming. Perhaps the most important lesson is humility. The universe is vast and life is subtle. Evidence that truly shows biology will withstand scrutiny. Until then, caution must prevail. Extraordinary claims deserve extraordinary evidence and extraordinary discipline in the way that evidence is gathered, tested, and shared. In 1973, Francis Crick, one of the co-discoverers of DNA's double helix, and biochemist Leslie Orgel published a provocative idea. They suggested that life on Earth might not have arisen spontaneously at all, but could have been deliberately seeded here by an advanced civilization. They called this concept directed panspermia. Crick and Ordelard were not proposing alien visitation in the science fiction sense. Rather, they argued that if intelligent beings existed elsewhere, and if they wished to spread life across the cosmos, they might launch spores or microbes on spacecraft toward promising planets. Earth, they speculated, could have been one such target. Their paper was intended partly as a thought experiment, a way of challenging assumptions about life's origins. At the time, the idea seemed fanciful, but today, technology has advanced enough that the concept of seeding life is not purely hypothetical. Humanity has already sent spacecraft beyond the solar system. We are developing the ability to engineer hardy microbes tailor-made for survival. If we wished, we could conceivably design missions that disperse organisms onto other worlds. Directed panspermia remains controversial, more philosophical than scientific. Yet, the very fact that we can now imagine performing it ourselves gives the idea new weight. It raises ethical questions. If we have the power to spread life intentionally, should we? The argument in favor of directed panspermia begins with a sense of duty. Life is fragile, confined to a single planet. Earth has been struck by asteroids, shaken by supervolcanoes, and changed by ice ages. One day, the sun itself will swell into a red giant, consuming the biosphere. Some argue that if life is precious, we have a moral obligation to help it spread beyond Earth. Seeding other worlds would ensure that biology, and perhaps intelligence, continues long after Earth is gone. There is also the perspective of opportunity. The universe appears rich in habitable environments. Mars, Europa, Enceladus, Titan, exoplanets in distant systems. Many may lack only a spark. If life cannot begin easily on its own, then seeding might make the difference, turning sterile oceans into living ecosystems. To some, that is an act of creation, a way of giving the universe more voices. But the case against is just as strong. First, there is the problem of contamination. If alien life already exists elsewhere, introducing Earth microbes could overwhelm it, destroying unique evolutionary paths. We could erase what we sought to discover. Second, there is the issue of hubris. We barely understand our own planet's ecosystems, yet directed panspermia assumes we should engineer those of others. The unintended consequences are unknowable. There is also the ethical dimension of consent. No other species or civilization can agree to our actions. Seeding life would impose our biology on other worlds without permission. For some, this resembles colonialism on a cosmic scale, expanding not through curiosity but through presumption. Ultimately, the question of whether we should seed comes down to values. Is the highest good to preserve life at any cost, or to respect the independence of worlds, even if they remain barren? There may be no simple answer. What is clear is that the choice, once hypothetical, is moving steadily toward reality. As our technology advances, directed panspermia moves from imagination into the realm of policy, and with it comes a problem familiar to fans of science fiction: the prime directive. Should explorers interfere with other worlds, or should they leave them untouched? International agreements already address aspects of this dilemma. The Outer Space Treaty of 1967, signed by most spacefaring nations, forbids harmful contamination of celestial bodies. Planetary protection protocols are built around the same principle. Do not seed life where it might interfere with science or with potential native ecosystems. In practice, this means sterilizing spacecraft bound for Mars, Europa, or Enceladus. The idea of deliberately spreading microbes stands in direct opposition to these commitments. Consent is another thorny issue. If intelligent civilizations exist elsewhere, do we have the right to alter their future environments without their knowledge? Even if no intelligence is present, worlds themselves hold intrinsic value. A pristine ecosystem, or even a pristine desert, tells us something about the universe. To change it irreversibly without study could be considered a violation of cosmic heritage. On the other hand, some argue that non-interference is itself a choice with consequences. If life is rare, and we refrain from seeding, then countless potentially habitable worlds may remain forever sterile. Do we have a responsibility to act, even if no one can grant permission? This is the essence of the prime directive problem applied to real science. There are no easy answers. What is clear is that any discussion of directed panspermia must grapple not only with biology and technology, but with ethics, law, and philosophy. The question is not just whether we can seed life, but whether we should, and who gets to decide. One of the strengths of science is that its ideas must be testable. Panspermia and abiogenesis both make predictions, and by examining these, we can imagine how evidence might one day distinguish them. Abiogenesis, the theory that life began independently on Earth, predicts that the earliest organisms here will show unique solutions to life's problems. Their chemistry would be homegrown, reflecting conditions of early Earth. If we discover life elsewhere in the solar system, and it is chemically distinct, using a different genetic alphabet or a different chirality of amino acids, that would favor abiogenesis on multiple worlds. Panspermia makes the opposite prediction. If life has spread between worlds, we should expect continuity. Life on Mars, if it exists, should look eerily familiar. It should use DNA or RNA. It should favor the same handedness of molecules. Its cell machinery should overlap with ours, suggesting shared ancestry. Thus, the test is comparative. Alien life that is familiar would argue for panspermia. Alien life that is alien in its chemistry would argue for multiple independent origins. In this sense, The universe itself holds the decisive experiment. While we discover a second Genesis, either like us or unlike us, will tell us which story is more likely. If life is found beyond Earth, how would we compare it to ours? 3 markers stand out: genetic code, molecular chirality, and evolutionary trees. The genetic code is the set of rules translating DNA or RNA into proteins. On Earth, this code is nearly universal, shared from bacteria to humans. If Martian microbes were discovered with the same code, the chance of coincidence would be vanishingly small. That would point strongly to common ancestry. Chirality is another key. Earth life uses left-handed amino acids and right-handed sugars. If extraterrestrial organisms share this asymmetry, it suggests inheritance. If they use the opposite hand, or a mix, that would argue for independent origins. Phylogenies, evolutionary trees, could provide deeper confirmation. If alien DNA or RNA can be sequenced, scientists could construct trees to see whether Martian life nests within Earth's diversity or branches separately. Such analyses would reveal whether life here and there are siblings or strangers. Comparative biology offers a powerful test. It will not just tell us whether life exists elsewhere, but whether it is part of the same story or an entirely new book in the library of the cosmos. Another way to test panspermia is to examine the couriers themselves. Meteorites that fall to Earth are often contaminated, but space missions now bring us pristine samples from asteroids and comets. Each new return is a chance to search for prebiotic chemistry or even traces of biology. The Hayabusa 2 mission to Ryugu revealed uracil and niacin. OSIRIS-REx's Bennu samples contained phosphates and organics. These discoveries show that asteroids are chemical storehouses. Future missions will refine this picture, probing whether molecules become complex enough to cross the line into biology. Comic missions add another dimension. ESA's Rosetta spacecraft sniffed a zoo of organics from Comet 67P, including amino acids. A future sampler returned from a comet nucleus could settle whether these ices preserve molecules that approach biochemistry. And then there are interstellar visitors. Oumuamua and Borisov showed us that material drifts between stars. Though we did not capture them, future missions may be designed to intercept such travelers, sampling them directly. If one day we find biology, or even prebiotic chemistry, on an interstellar rock, it would be the clearest evidence yet that panspermia is not limited to our solar system. The couriers are testable. Each sample taken from space is another piece of the puzzle, telling us whether life's toolkit is common cargo in the cosmos. Mars is central to the panspermia debate. If life exists there, or once did, it could share ancestry with Earth. That is why the upcoming Mars sample return mission is so critical. It aims to bring back sealed pubes of Martian rock and soil collected by NASA Perseverance rover and return them to Earth laboratories. The challenge is twofold. First, contamination must be prevented. The samples must remain untouched by Earth microbes to preserve their integrity. Sterile handling facilities are being designed with unprecedented stringency, clean rooms within clean rooms, with robotic manipulation to avoid human contact. Second, biosignatures must be unambiguous. Scientists will look for cell-like structures, but morphology alone is not enough. Chemical evidence is required. complex organic molecules, isotopic patterns favoring life, or even genetic material. These signatures must be proof against alternative explanations. If Martian samples reveal biology similar to ours, panspermia gains support. If they reveal biology utterly different, abiogenesis gains support. If they reveal nothing, the question remains open. Either way, the results will be transformative. Mars sample return will provide one of the most direct, falsifiable tests of weather life. And its possible spread exists beyond Earth. Beyond Mars, the icy moons of the outer Sova system may hold answers. Enceladus, with its geysers spraying water into space, offers an extraordinary opportunity. Cassini's flybys revealed salts, organics, and phosphates in the plumes. Future missions could fly through again, this time with instruments tuned for biosignatures, mass spectrometers capable of detecting amino acid distributions, lipid-like molecules, or even complex polymers. Europa, too, may have plows venting from its hidden ocean. If confirmed, spacecraft could sample them directly without drilling through kilometers of ice. The beauty of this approach is its cleanliness. By sampling material already ejected, we reduce the risk of contamination, creating what some call clean rooms in the sky. The challenge is sensitivity. Biosignatures are subtle, and ambiguous signals are dangerous. Instruments must discriminate between abiotic organics and genuine signs of life. They must also avoid Earth contamination carried inadvertently on spacecraft. Proposals such as NASA Europa Clipper and future Enceladus missions aim to meet these challenges. Imagine the implications. A spacecraft flying through a plume, detecting biomolecules with the same handedness as ours. That would be a powerful hint of shared ancestry supporting panspermia. Detecting molecules with opposite chirality would be just as powerful, pointing to an independent origin. Ocean world plumes represent one of the most exciting near-term opportunities to test panspermia. They combine accessibility with chemical richness, offering a chance to sample alien oceans without touching their surfaces. Each plume particle could carry a message, a whisper from a hidden sea, telling us whether life is a local miracle or a galactic traveler. If panspermia is true, then all of us are cosmic migrants. Our ancestry would not begin in Earth's oceans, but in a rock, a comet, or perhaps a distant star system. Every cell in our bodies would carry the mark of a journey across space, a thread tying us to other worlds. In that view, life is not confined to Earth, but is part of a galactic family. Somewhere out there, our cousins might exist, shaped differently by their worlds, but sharing the same distant origin. And if panspermia is not true, if life arose independently here, the story is no less profound. It would mean that chemistry on Earth crossed the threshold to biology without any help from the cosmos. It would prove that the universe allows life to emerge not just once, but potentially countless times. Independent gemesis here suggests that it could happen elsewhere too, wherever conditions are right. In both cases, whether we are seeded or self-made, the conclusion is the same. Life is not an impossibility. It is a natural outcome of the universe written into matter itself. No matter the verdict, panspermia leaves us with wonder. The cosmos is restless with chemistry. Meteorites fall carrying amino acids. Asteroids hold nuclear bases and phosphates. Ocean moons vent geysers, filled with salts and organics. Everywhere we look, the building blocks of life are present. This suggests that life, or at least its precursors, are not rare accidents, but recurring themes. The universe seems predisposed to complexity. Molecules assemble, reactions repeat, and structures self-organize. Whether these processes culminate in biology depends on conditions, but the stage is always set. For those seeking comfort, this view is generous. We do not live in the barren void, but in the cosmos fertile with potential. Even if we never confirm life elsewhere, we know that the universe is constantly experimenting. Each comet, each asteroid, each cloud of interstellar dust carries the possibility of chemistry, stepping one move closer to life. The question is not whether the cosmos is alive, but how many of its seeds have bloomed. And now, as you drift towards sleep, let us step back and see the story as a whole. Picture a grain of dust floating in the dark between stars. It is small, insignificant, yet it carries within it the potential for something astonishing. On its surface, ultraviolet light rearranges simple molecules into amino acids. Ice coats it, protecting its fragile cargo. Over time, it joins countless other grains, gathering into comets and asteroids. These bodies travel across the solar system, some colliding with young worlds. On Earth, one such collision may have delivered the chemistry that tipped the balance toward life. Out of dust and rock, oceans filled with molecules that began to replicate, to adapt, to grow. The long chain that leads to you began with collisions and waiting, with dormancy and chance. Whether seeded from afar or sparked here alone, the story is one of patience, resilience, and the quiet creativity of the cosmos. Tonight, you are part of that story. You are stardust that dreamed of oceans, oceans that dreamed of cells, and cells that dreamed of thought. In you, the universe has found a way to wonder about itself, so that the questions linger as you rest. Are we children of Earth, or children of the stars? Do our cousins wait on distant worlds, or are we one of many beginnings scattered across space? The answers will come slowly, as missions return samples, as probes fly through plumes, as telescopes search the skies. For now, you can simply close your eyes knowing that whether seeded from beyond or born of this earth, you are part of a universe endlessly fertile with possibility.